Welcome back. Today, we are going to seriously level up our predictive powers. We're moving on from those simple one-to-one relationships and diving headfirst into the real world. You know, the messy, complicated, fascinating world, where pretty much everything is caused by many things working together. So, get ready to unpack the powerhouse that is multiple linear regression.
Okay, so here's our game plan. First up, we're going to see why just one variable is rarely, if ever, enough to tell the whole story. Then, we'll decode the secret recipe behind the model itself and its powerful engine. After that, we'll walk through the essential rules you absolutely have to follow, learn how to grade your model's performance, and finally, we'll spot the common traps and see what amazing tools come next. Let's get right into it.
So, why do we need to make things more complicated with more variables? Well, because reality is messy. Trying to explain some big, complex outcome with just one single cause? That's kind of like trying to paint a masterpiece with only one color. It's not just a simple mistake, it can be a recipe for some seriously misleading conclusions.
I mean, think about it. Could you really predict a company's sales using only their ad budget? What about seasonality? Or, your competitor's huge sale last week? Or just the general state of the economy? If you ignore all these other crucial factors, you're basically trying to solve a puzzle with half the pieces missing. Simple regression is a fantastic starting point, for sure, but multiple regression is where the picture truly comes into focus.
And here it is, the big upgrade. You can see it right here on the slide. We're making a huge leap. Over on the left, you've got simple regression, one cause, one effect. But on the right, that's the powerhouse. Now, it might look a little more intimidating, I get it, but the idea is actually brilliantly simple. We're just adding more ingredients, more of those X variables, into our predictive recipe. And the result? A way more accurate and insightful answer. It's time to level up. All right, ready to peek behind the curtain? We're about to demystify that big formula you just saw. We're going to break down every single piece and then uncover the genius behind how it all works, a method called ordinary least squares. Let's dive in. So, just imagine this equation is a secret recipe. That y is the amazing dish you're trying to create. The β₁, that's your base, your starting point. Now, each of the other beta coefficients, those are your special ingredients, and each one adds its own unique flavor. And here, this is the model's absolute superpower. It lets you taste the impact of each ingredient individually while holding all the others perfectly still. This is the power of ceteris paribus, and it's what lets us isolate the true, unique effect of every single factor. It's incredible.
So here's the million-dollar question. In this huge universe of data points, how does our model find that one perfect recipe? I mean, out of all the infinite possibilities, how does it choose the ideal combination of those beta coefficients to make the most accurate prediction possible? Let's find out.
And here's the answer, just beautifully visualized. We're not just drawing a simple line through our data anymore. Nope. We are now fitting a multi-dimensional plane that weaves through all those points. This is the magic of ordinary least squares, or OLS. Think of it like a master sculptor who's meticulously carving a surface that gets as close as possible to every single data point. It creates the perfect fit by making the sum of all those little red lines, the errors, as small as mathematically possible.
Okay, this next part reveals the secret behind why OLS is so legendary. Thanks to this beautiful piece of math called the Gauss-Markov theorem, as long as we follow a few key rules, OLS becomes the undisputed champion of linear models. It's blue, the best linear, unbiased estimator. Unbiased just means it hits the bullseye on average, and best means it's the most precise, most reliable tool in our entire statistical toolbox.
But, and this is a huge but, with great power comes great responsibility. To unlock that blue guarantee, you have to follow a strict set of rules. Think of this as the mandatory pre-flight checklist for your model. And you really don't want to ignore these rules, because a flawed model can lead to some disastrously wrong results.
So, let's run through that checklist. First, your variables need a linear relationship, no weird curves or U-shapes. Second, your predictors have to be independent voices, not just echoes of each other. That's a trap called multicollinearity we'll talk about in a minute. Third, your data point should be independent, like a room full of strangers, not a family where everyone's influencing each other. And finally, the errors need to be well-behaved, with a constant variance and a nice normal distribution. You break these rules and your model's credibility just vanishes. Okay, so we've built our model, and hopefully we followed all the rules. Now it's time for the moment of truth. How do we know if our creation is a masterpiece or a total dud? It's time to grade our model's performance and see if it actually makes the cut.
The star of the report card is usually R². It's the simple number that tells us how much of the story our model can actually explain. An R² of 0.7 means our model accounts for 70% of what's going on. Sounds great, right? But here's the catch. R² only tells you how much you can explain. It doesn't tell you how wrong your predictions are on average. For that, you need to look at metrics like mean squared error, or MSE, and its friendlier cousin, RMSE, which tells you the typical error in the same units you were trying to predict. A good model needs both a high R² and a low error. But there's a hidden flaw in our star metric that we've got to talk about.
What if we get greedy? What if we just start throwing more and more variables into our model, hoping to nudge that R² score a little bit higher? What if we're just adding noise? Well, here's the scary part. R² will never tell us we're wrong. It almost always goes up when you add a variable, even a useless one, and that creates a really dangerous false sense of security. It's a trap, and we need to know how to avoid it.
But don't worry, because we have a secret weapon, and this slide shows it perfectly. Adjusted R². It's like a wise mentor that guides us away from making a bloated, overfit model. It rewards us for adding truly valuable ingredients to our recipe, but as you can see with those red triangles, it actually penalizes us for adding junk. It's our essential shield against the dangers of an unreliable model.
So we've unlocked this really powerful tool, but we also have to be super aware of the potential pitfalls. Let's explore one of the most common traps, multicollinearity, and then discover the advanced techniques that can save us when the basic rules of regression get broken. The journey is definitely not over yet.
Remember that no multicollinearity rule from our checklist? Let's really break that down. It's like having two friends in a meeting who always say the exact same thing. They aren't adding any new information, they're just creating confusion and noise. And in the world of regression, we need our predictors to be independent voices, each one telling a unique part of the story.
Okay, check out this sudsy situation in the data here. We're trying to predict the amount of foam based on two different soaps. But wait a minute. If you look closely, soap 2 is just soap 1 times 2. They're basically twins. Our poor model is now in a state of utter confusion. It has no idea how to tell which soap is the real bubble-making champion, and our results become completely unstable and totally unreliable.
So when your model has this kind of identity crisis, your software is going to sound the alarm. As the source material puts it, it will spit out trouble. It's basically going to throw its hands up in defeat, unable to figure out the unique impact of each variable. This is your big, bright red flag, your signal to step in, find the redundant variable, and take it out.
But here's the good news. For pretty much every problem, there's a solution. Statisticians have a whole toolkit to handle these violations. We can transform variables to handle curves. We can use advanced techniques like ridge or lasso regression to fight multicollinearity. We can even tame wild outliers with robust methods. The key takeaway here is that this model is just the beginning of a journey into a really exciting world of predictive modeling.
And that brings us to our final, crucial question. We've seen the incredible power of multiple linear regression in unraveling these complex, straight-line relationships. But what happens when reality throws us a curveball? What if the relationship between our variables isn't a straight line at all? Well, that's when we venture beyond, into the thrilling world of nonlinear models and polynomial regression, a world of even more possibilities. But that, my friends, is a story for another time.